Okay, hi everybody. Like Dr. Wagner said, I'm John Morris. My dissertation defense is on a new mathematical framework I've developed called a constraint hypergraph. I'm hoping to show today how it can be used to enable universal system simulation, and especially show how it's a solution for model-based engineering and for forming digital twins. Quick bio, if we can get things working correctly. I always work until you start the presentation. Okay, we'll go on this. Quick biography of myself. I was married in 2018 and finished my bachelor's in 2021 at Brigham Young University in Provo, Utah. In 2021, I came here to Clemson and started as the PLM applications engineer, where I'm involved with a lot of our digital engineering initiatives, trainings, workshops. We taught a class on PLM in 2023. I had 3 sons born here while I was at Clemson, one in 21, 23, and then one in 2025. I got my master's in 23 en route. I've also done several collaborations with the Naval Postgraduate School in 2024, working with digital twins with them. We'll see a little bit of that work in this presentation. I also was a visiting researcher for a month and change at the National Institute of Standards and Technology. And then, if all goes well with this defense today, I am moving on to a postdoctoral fellowship at NPS. We're also working on some collaborations with the Alan Turing Institute in the United Kingdom, and then I'm looking for a tenure-track faculty job starting in the academic year next August. So that's me, and now ignoring me, we can go on to the presentation. I want to motivate this a little bit by saying that the work of science and engineering is to describe the world. We have all these worlds in weather and nature and rockets and urban systems, and all these things are things that we need to know about. If we want to interact with them, if we want to design them, if we want to make them do things that we need to live as humans, then we have to be able to describe them. And that is the work of science, is describing their behavior. In order to do that, we have to know a lot of different things about a lot of different areas. For instance, if I wanted to describe this airplane, I might need to know a little bit about its combustion, about its thermodynamics, the materials used in it, the economics of driving it, the ergonomics of the pilot and the passengers, its capacity and geometric dimensions. All these things are information that are in different domains, but I need to have all those domains come together in order to understand the behavior of the collective system. To do so, we usually come up with lots of different models. And all these models represent different parts of different domains, but they're difficult to integrate. They represent our siloed parts of a system where we don't always get the interactions. It might be hard to see how designing a circuit diagram in one way is going to impact the geometry of my electronics box, or how the FEA analysis is going to impact my project scheduling on my Gantt chart. All these models represent the domains, but we need a way to bring that information together. So what I've done is created a new framework called a constraint hypergraph. This framework allows us to take information no matter what domain it's in and what system it's a part of and reconcile it into a single model. I'm going to show how that model can be used not just to represent a system, but also to simulate and describe that system fully, get any information out of the system that we might need to know as a scientist or an engineer. Here's a little breakdown for this presentation. We'll start by defining a CHG. I'll tell you how we've defined it, how I've gone through, and what different structures make up a CHG to make it useful. Then I'll show how it can be used for declarative simulation. I'll also define what declarative simulation means, and then talk about why declarative simulation matters. And then finally, I'll show the applications of this. If we have this framework, what can it be used for? And we have 2 exciting applications that we've worked on, model-based engineering and then digital twins, and I'll show that at the last. But starting off, first off with our introduction to constraint hypergraphs and what they are. So I'll start from the very basics so we can drive up what it means to represent any system anywhere. First off, a system is, according to Ross Ashby, just a collection of variables. That is, a system is all the things that we can know about a system. So if I have this plane, I'm able to know its color and its name or fuel capacity. These are all different aspects that I can distinguish about this plane. And by setting up these 4 things, which might be states or variables, we can say that these are the 4 things that make up my system. So there's a lot of stuff in this plane. I can go deeper and deeper and higher with higher fidelity. But the point right now, my system is 4 variables. These 4 right here, this is what I distinguish as different parts of this airplane. We represent these in real systems as sets of values. So the color can have sets of values that might range over. The fuel capacity could be any real number or positive real number, so on and so forth. Each one of these becomes a state that has some kind of value. And for this to be a temporal system, those values can only express, or those sets can only express one value at any given frame of reference. I can say that this plane can either be a galaxy or a globe master, but not both at the same time, according to how I've broken down my system. We want, as engineers, again, to observe and describe this system. There's two different ways that we can describe a system. The first is by observations. Observations are when I go through and I actually make a measurement in my system. So I go through and say, this system, this plane is gray. I can observe that, measure it. Or if you know your planes, you might be able to say that this one is a C-17 Globemaster. That's a measurement that you can make as a human observer. However, there's many things in our systems that we cannot observe, either because it's hard to do so, we don't have the tools to measure them, or because they don't actually exist, they're not available to us. That's a lot of times with states that are in the future or in the past, times that we actually can't go out with a tape measure and get a measurement for that. In those cases, we cannot make observations. What we have to do is make simulations. Other words for simulations are inferences or predictions or even estimations. But when we do with a simulation, our main definition is that we have information that we can observe, and then we have some kind of model that allows us to relate those observed facts to some other state that we want to simulate. So again, a simulation is some kind of transformation from inputs to outputs, right? Things that I know to things that I want to know. And we represent those transformations with these relationships. Those relationships mathematically can be described as algebraic functions. That is, that they take every value from one set and map them to a value in another set. So if I give you a function here that takes name and mass to capacity, then I say for every single one of these airplane names, I can tell you the fuel capacity. Maybe I have some database that I look those up or some table that gives me from. Representing these algebraic relationships in this way allows me to describe the system's behavior. And this really comes back down to the work of Jan Willems back in the late 1900s and then early 2000s over here, where he was able to say that the behavior of a system can be represented as functions on a system. That is, if you take all the different states that a system can be represented as possessing, the behavior of that system is the constraints on those states. And we can represent those constraints as functions here. So this is a representation of a plane's behavior. That is, C-17s always behave or are constrained to behave as having a fuel capacity of 130,000 liters. Because they're functions, we can represent multiple different arguments. So here I can have a function that takes in economy, and fuel capacity, and gives me like the flight range. I would just divide capacity by economy for this mapping. 130,000 divided by 11 is about 12,000 kilometers. That's the flight range of this Globemaster. When I have these functions, I can have these multiple inputs, and you'll see how this is multiple arity. Here, the domain of this function is not just the economy set or just the fuel capacity set, but rather the Cartesian product of these two sets. And that's an important thing to take note of. We're actually saying that every ordered pair of economy and capacity gets mapped to a flight range. Specifically, if you give me an economy, you give me a capacity, for every single one of those combinations, there's a range that I can calculate based off of this function. So there's the mapping that I'm giving. There's something interesting that we can do with functions that is extremely important to understanding these systems, and that is that we can make them compose. So any function whose domain is given by the codomain of another function can be composed to form a whole new function. Here's what that looks like. So here I have a function here whose domain is economy and fuel capacity, and this function's domain is name. They meet in the middle over here, and I can take those and compose them to form this new function, which maps every name to a range for these planes over here. And you can see that this is the same behavior that we already had, but by composing the functions, I've kind of shown the relationship between name and range, where before, with these individual ones, that wasn't readily apparent. So the composition of functions gives us new insight on the interactions of all these different elements. Okay, with this understanding of nodes, relationships, and functions, we can now build our first constraint hypergraph. So a constraint hypergraph is a description of a system. All the information of the system gets represented as nodes. We have the same nodes that we saw before over here and a couple others over here. Those nodes, again, are sets. They're sets of values where every expression of a set is the current state of that system in the frame of reference that we're considering it in. And then secondly, those functions, those behaviors, are represented as edges. And because functions can have multiple arguments, we don't just get normal edges, we get hyperedges. So this is not just a graph, it's a hypergraph, where every single function shows the mapping between one variable or a set of variables to another one. This is our hypergraph. These are the most basics, and because we've gone very basic, what we can say is that every system can be represented this way. Every system is just those sets of variables, and every behavior is a set of functions. And so every system, no matter how you express it or what you're considering or what domain it's in, can be turned into this set of nodes and edges. Okay, something else that's really important with this is that we've turned our functions into simulations. So again, a simulation is something that turns an input or a set of inputs to an output. Here, our functions do the same thing, but not just the individual functions, but also the composition of those functions represent even more simulations. So what do I mean by here? Here I have a graph, If I take it and I told you that I know the name of this aircraft, this function tells me that I can also tell you its fuel capacity. There's some mapping between name and fuel capacity, which we've already seen. Here's that path represented here, taken from the hypergraph, so you can see that path. We can also have a path that takes the loading of the airplane and the speed of the airplane and maps it to its fuel economy. If you tell me how much it's carrying and how fast it needs to go, I can tell you how efficient it's going to be, let's say. You'll notice that this path is not just a chain. In a normal graph, paths are chains. In a hypergraph, they're actually trees. They have leaf nodes, which represent our inputs, and they have a root node, which represents our output. I can also have a similar path. This is E and C to R, so this is economy and capacity. Gives me range, again, that same relationship we saw. But then, now that I have these individual paths, I can bring them together to get composition paths. So if you tell me the plane's economy and the plane's name, I can simulate its range based on those inputs. And the same with knowing its loading and speed and capacity, and loading speed and name. Both of those can be used to simulate range. These are different simulations that can form on this graph. Notice that even though we only have 3 edges, we have 6 different simulations that we can form from this, 6 different ways that we can understand our system, even outside of just straight observation. What we like to emphasize here, what I want to emphasize, is that what we've done is we've embedded behavior in the framework. With a lot of frameworks, what you have to do is you have to bring knowledge in order to form the simulations. But because we baked this behavior into how the model is formed, we can actually bring these simulations out without having to bring our own knowledge to the table. And what this means is we've created a way for declarative simulation. And because this is such an important point, I'm going to belabor this a little bit and define declarative simulation. So here's my, well, you can't see this. This is a map of America. Here's my little model analogy for understanding declarative simulation. So here, if I wanted to say I was a traveler and I wanted to travel from Los Angeles to New York, I might have 2 different ways that you could tell me how to get there. The first one is an imperative way. That's where you go and give me all the steps for traveling from one place to another. So you say start in LA, then go to Denver, then go to Chicago, then go to New York. If I follow those steps, I will arrive at New York. It's a good path, it gets me there, it gives me that information. However, you've not told me anything about how the actual system of trains or buses actually behaves. I don't know it from these steps. If I'm traveling, I need to make different decisions. I don't have any information I can make those decisions off of. My only choice is to go to the next step. That's the only thing I can do. With the declarative system, I don't give you a route to travel. Rather, I give you a map of the system, and I allow you, as an intelligent agent, to make decisions about how you want to get there. You could travel from LA to New York, or you might detour around Chicago and go through Atlanta. Maybe there's a train down or something. But as an intelligent agent, you can make those decisions. What the map gives you, that the directions don't, is the ability to make decisions on the model. Or in other words, it gives you the behavior of the system, and you can interpret that behavior to understand the system in different ways. We can do the same thing in a CHG. So normally, imperative processes are just giving you a path. If you wanted to form a simulation between E, C, and R, well, great, here's a path for that. There's the path, you have the path, it does work for as a simulation. But if you wanted to form different simulations, if you want to understand other parts of the system, if you wanted to see the behavior and the relationships, all the interactions, you need a declarative model that has all those paths baked into it. And of course, in addition to having that declarative model, you need to have some kind of agent, whether a human or a robot, that can actually go through and find those paths. What we've done is we turned declarative simulation into a pathfinding operation. Anything that can find paths can form these simulations. To motivate what this does for us, here is a little complex graph that shows you what is the worst case scenario for how many simulations you might have to form for a system. So for a system of n variables, you might have to write up to a little over 2 to the n different simulations. This says that if you have a system of 25 variables, you might be writing 400 million different programs. That's definitely a worst case scenario. You're not going to write 400 different million programs, but it is the maximum number of simulations you could write. That's 400 million different MATLAB scripts. That's 400 million different Python scripts, or 100 million, or whatever it might actually turn out when based on how we combine our things. Versus a CHG, where you can get all these paths out of a single representation with, I don't know, 500 nodes in it, 600 nodes. What we're doing is taking exponentially ordered complexity and reducing it with this declarative framework to linear order complexity in most cases. It's not actually a firm bound, but it's a soft bound there that we generally get linear case performance on this. Okay, so that's what we get with the CHG. It is a method for declaratively embedding behavior about a system so that you can represent any part of a system that you might want to do these kind of big simulations. The next part that I want to focus in on is what we need to do in order to enable those simulations. Again, we talked about how to find a simulation, you have to do pathfinding. If you have some pathfinding agent that's looking for all these paths, what do they need to consider in order to actually make these simulations work, or especially whether they need them in order to represent real systems. There's 3 different wrinkles that come out of a CHG that we have to consider in order to make them actually work. And so we've gone through and broken these down, figured out what they are and how they need to be formulated so that our agents can actually process them for pathfinding. The first one is partiality, the second one is cycles, and the third one is multi-edges. And I'm going to take these step by step and give some motivating examples. So here is partiality. Let's say I have some pipe, maybe a pitot tube on my aircraft, and I want to understand the pressure loss across that pipe. Well, I can use the Darcy-Weisbach relationship to, and you don't care about the mathematics, but to give this constraint hypergraph, which tells me that if I know the diameter and length of the pipe, and also the velocity and viscosity of the fluid, I can tell you the change in pressure. Great, there's my relationship. However, there is a condition on this relationship, and that is that this relationship over here, this formula, only holds if the flow is laminar. We can represent laminar with the Reynolds number and say that the flow is laminar if the Reynolds number is less than 2300. When we have this, what we're saying is this relationship is good, but it doesn't work in all cases that we want it to. There's some kind of validity frame that we need to incorporate into the graph. How do we represent that validity frame? Well, let's go into the mathematics to understand it. What we're really saying is that of all the values in our input set, we only have a mapping for some subset of them. That's the definition of partiality. It's a function that only maps between a subset of the full domain. And so you can see here, I bring Reynolds number into the domain. Here's the ordered pair of all these different values. I might have lots of different lengths and diameters and whatnot, but I also have different Reynolds numbers. And what I'm saying with this partiality is that this function, the Darcy-Weisbach relationship, only maps ordered pairs where the Reynolds number is less than 2300. If it's greater than 2300, I don't have a mapping for that. So this function is only partially defined, and I'm going to show that with this dotted line over here. So not every single value of Reynolds number is mapped. What this does for us is it gives us some unfortunate characteristics with how we can simulate our systems. If our system doesn't have any partiality, everything is mapped, then we can say all our functions compose. And we can solve our graph, optimize it for the best possible paths. We can find all the paths in it, find all the different simulations, pull those out and say these are the best simulations. The best way to get between this node and that node is along this path, and that works great, and it'll always work in every case. But as soon as we bring partiality into it, suddenly some of those paths don't work for every single input. So rather than being able to pre-solve our graph, we actually have to go at runtime and plug in values and say, is this input in the domain of this function, or is it in part of that excluded subset? And because of that, we lose the ability to pre-solve our graph. We actually have to solve it at runtime based off the inputs that we provide. That is unfortunate, but it is not going to inhibit our ability to use these hypergraphs. And I also show that partiality enables quite a bit more in terms of the expressiveness of these graphs. One, we can capture this relationship, which before we couldn't capture that validity frame. With partiality, we can. But 2, we can also enable cycles. What is a cycle? Well, here's another example. We have this plane. It's starting at this position x0. I want to calculate its position at 2 more time steps, x1 and x2. So here's my 2 time steps for my plane. I want to calculate that. If it's moving at a constant velocity, the relationship between these is not hard to compute. It's just the previous position plus some constant offset v times t, where t is my time step. I can represent this with a hypergraph, and this is a perfectly good hypergraph. This says that if I want to simulate x2, I need to know x1. And if I want to know x1, I need to know x0. And obviously, I always need to know vt, and I just add those together. And I can run this hypergraph and get a simulation. The question for you then is, what if I wanted to simulate x3 or x4 or x sub n for some arbitrary distance? Well, in that case, I'd have to construct a new hypergraph in this case, right? Add another node, another relationship, and that would be another new hypergraph, and keep going on and on and on for every single set of n. We don't have a way with this just to show the general relationship between x and the previous value of x. But that is what we really want to get. We really want to show the relationship of x sub I is equal to x sub I plus n plus this vt. To do that, we have to have a cycle. Cycles do not exist in the real world. The real world is modeled here as causal, and if it's causal, we cannot say that this thing depends on itself in order to know it. You cannot have to know something in order to know something. That doesn't make sense. But what we can do with our pathfinding agents is say, if there's a cycle, do not interpret it as resolving for the same node. Rather, what we're going to do what's called unraveling. This is a mathematical term from category theory. We take these cycles and we break them out into these more elongated graphs. So this says every single time you go through this cycle, see this edge where xi is in the domain of itself? If you go along the edge and resolve for xi, then treat that node as a new node, x sub I plus 1, and do all your math on that new node as if it was completely distinct from the original one. If we do this unraveling, then we can actually form these arbitrarily long graphs. So we captured all the relationships between x0 to x of n in a single cycle in our graph. In order to have this cycle, and in order to pathfind it, we actually had to have one more thing, which is an exit condition. The pathfinding agent will go through and continually resolve this, but at some point it has to know when that node is the node that we want as the output. When does it reach x sub n? Well, the way to do that is with partiality. So this is why partiality is important. Partiality says that there is a relationship between x of I and x of n, but not every x of I is x of n, just some of them. And if we can express that which ones are x of n, the ones where I is equal to n, then we can say, go through this cycle as many times as you need to, but once you are able to run this node, then there's a path that will be this unraveled cycle plus this edge that will arrive at x of n. And now suddenly we can solve this kind of iterative cycle. One thing I'll add to this is that a cycle represents behavioral patterns. It's when a system behaves the same way over multiple different nodes. That's what we're trying to express here. And this happens a lot in time series dynamic systems. It doesn't have to be a dynamic system, but it often occurs in time where the system's behavior does not change or evolve even as the states evolve through as time goes on. Okay, our third structure we need to talk about is multi-edges. These are ones that indicate competing models. This is when I have two models that allow me to solve for the same thing. They are all both viable, they're correct models, but usually one of them can be used for a simulation. I cannot have a simulation process with two values for the same node. I have to pick which one I want. So for instance, I might have a model that runs some FEA analysis. It's a long, burdensome ANSYS solution that comes up with a pretty accurate value for t based off of s. And I might have a large language model like ChatGPT where I just say, here's my bending load on my wing, tell me how much it's going to bend by, and it gives me a good guess at it. The ChatGPT model is a lot faster, but it's a lot less accurate. But they both allow me to simulate t. What I want to do is not just model different behaviors here, but now I want to model my own modeling preferences. Which one of these models do I prefer? Well, it depends on if I want accuracy or maybe computational time. These are preferences that are outside of my system's behavior, but which I need to pass to my Pathfinder for it to solve it. The way we do that is by passing weights to the system. Weights represent some kind of grading, right? It's a cost here, or at least some pre-order that we've established for our edges to say that the cost of running this edge is about 2.5 times as much as running the first edge. So when the Pathfinder comes to it, it can run the one that it prefers the most. Now the nice thing about edges is that we haven't said that these edges are bad in any way. If the ANSYS edge is not available, maybe it doesn't meet the partiality constraint, or we don't have access to ANSYS at some point, if it's not available, we can still run ChatGPT. We're just saying that we don't prefer to with this given context for a simulation. Okay, so what we've done is we've established THGs, we've defined them, and we've given 3 different structures. That is cycles, partiality, and multi-edges. And we've said that with these things, we can now represent any system. And furthermore, we can autonomously derive simulations on those systems. Let me prove that with a brief demonstration. So this is a demonstration on a pendulum system. It's a simple system, but it does have nonlinear behaviors. But luckily, we understand those behaviors a lot as engineers, so it's a good one to understand what's going on here without being lost in the physics. So here's our pendulum. It's a simple pendulum. It's got 3 dynamic states: acceleration, omega is velocity, theta is position. It's also got some constants in here. Gravity, radius is the length of the tether. This is a constant time step over here. You can see we also have 3 behaviors. The relationship between alpha and omega is this integration, right? We integrate acceleration to get velocity. This is a first order Eulerian integration. It's about as simple as you can get for integrators, just to keep things simple again. But we're just taking the previous value of omega and adding this constant offset to it. The same thing happens for integrating omega to get theta. We have this first order Eulerian integration. And then over here we have our equations of motion. This says that acceleration is equal to the sine of theta times the negative gravitational acceleration divided by r. That's our system. It's this nice little triangle. You can also see we have this cycle, right? As we solve for theta, alpha, that allows us to solve for omega, then theta, and then back up again, and we can repeat this cycle and keep going around. In order to do simulation on it, we need to provide our agent. That's an agent that can do pathfinding. In this case, I have coded up software called Constraint HG. This is an open source Python package. You can download it from the pip package index, which means if you are doing Python, you can go pip install Constraint HG. There is nice documentation on here. I strongly recommend you go check out this documentation. It goes much more into depth into what this software is, everything about how you can use it. It gives lots more complex cases than what I'm going to be presenting here today. But this is the software that we've written, and which is under review right now with some software review. What it does, what we provided methods for with this software is first the pathfinding. We have a way for doing declarative simulation and discovering paths, but also for representing the CHGs in the first place and visualizing them. We have ways to print out the paths that we're looking for and the different cycles that we're discovering. And we have ways for forming cycles, the partiality, and the edge weights. All these things are tricky, right? You have to have some method for taking them in, incorporating them, and solving problems. For instance, how do you handle nested cycles, or cycles that cross between each other, or loop cycles where one cycle lives inside of another one? Those are really difficult circumstances, but we've gone through and broken out how all those are going to work and how we're going to be able to solve all of those cases. And then also, of course, we have extensive logging tools. These are pretty difficult to debug, so we have lots of ways to look under the hood. We've been pretty explicit with our documentation and our exposure of information to make these as usable as possible. Okay, so let's take Constraint HG and let's use it to simulate our system. The process first is we're going to make our CHG, so we're going to identify system nodes. Then we're going to form relationships between them. Then we're going to pass that to the solver. The CHG solver is going to take those and construct the constraint hypergraph for it in the code and work with all those relationships. Then all we have to do is request simulation. This is a big part with declarative simulation. We just have to say, I want to solve this thing. This is what it looks like with the pendulum. Again, with declarative simulation, we only have to specify the start and end points. You don't have to specify how to get there. You just say, I want to get here, and the agent can autonomously find the path there. So here on my solve command, here's the hypergraph. We're going to call the solve function that is in Constraint HG. It takes in a target, I want to know theta, and it takes in the inputs. These are the things that I know. These are our starting conditions for our pendulum. And then I'm going to also give it an index that says I want to know theta at its second index of the cycle, or in this case, it happens to be the second time step of our simulation. This is all I need, and then I get a simulation that autonomously pops out, right? I don't have to write the program that actually makes a simulation. I just have to say, here's what I want, and it will write it for me. This is the outputs, a little verbose, but it's fully formed path. This is an unraveled cycle in our hypergraph. So it starts over here. These are our inputs. If we know G, theta, and R, from here, our inputs over here, we can pass those into an edge, this edge, to calculate alpha. And this is alpha, and it's going to be the second index of alpha, actually. We know that at the second time step, alpha is negative 27.74 radians per second squared. Then if I know alpha, I can use alpha, delta t, and omega in this edge over here to calculate the second time step of omega. The velocity of our pendulum is 0.55 radians per second. And then if I know this omega, I can pass that delta t and theta into this edge right here to get out our second index of theta, which is 0.7739. Again, this is a very simple simulation. We've only done 3 edges here, but I've unraveled my cycle to form this arbitrary simulation. I could run this again for 100 cycles, for 1,000 cycles. I could be calculating alpha or omega or G or R or the time of the series, whatever I want. But I just pass those information in, and it will find the simulation for me, rather than me having to go through and write a big, long script in MATLAB that will actually calculate it. This is cool. There are some limitations. First off is that the way that the Constraint HG software works is it does a breadth-first search. So it actually is going to exhaustively search every single possible path from our input space to our output. This works. It always finds a path and always finds the right path, the best path, but it's kind of slow. And when I say slow, it's not terribly slow. We can run complex systems with 600 nodes and lots of edges in the order of seconds, not even over into minutes. But it is not microseconds, which is what we would kind of want. So before this is really ready to be plugged into a company's software, we do need to figure out a little bit faster ways to do our searching than this breadth-first search. And then, of course, because of this partiality, we can't pre-solve our graph. So we have to solve it for every single input. You give me an input, I have to find that path. I can't just tell you, here's what the path would be. It has to be found at runtime. So a little bit of limitations here, but again, still showing full consistency with finding our best simulations. Okay, we have our CHGs, we know how they work, we know they can represent any system, and now we have a pathfinding agent that can actually trace out these paths and perform simulation for us. Now the question is, why do we want these things? Why do we care about it? I want to show 2 applications that really drive home some of the use cases of this declarative universal simulation. These 2 use cases are model-based engineering and digital twins. In both of these cases, what we want is the ability to take models and use them usefully. We want models, first of all, that can exist in different contexts. So if I have a model of a tire, I want to be able to use it from Joe and Bob and Abby. And if I have a model of if I have it on different softwares, I want it to work on different computers and with different companies. I want to be able to email my CAD and have it work on somebody else's system. The other thing we want is we want models that work together. If I have a model of a tire and a model of a car and a model of a road, I want those to come together to give me a model of a driving system. I want that to be a good model. I want it to work cohesively. All those domains should come together. Now we can do that now with constraint hypergraphs. And I should have done this earlier, but let me just motivate this with a little bit of a mathematics behind here. When we say we want to see how these things interact and engage, what we're really saying is we want mergers of two hypergraphs. A constraint hypergraph represents a system. The merger of two hypergraphs represents the mergers of those two systems, the system aggregation. Here's what this looks like. So we might have a graph. We've seen this graph before, but if I'll break it into two different graphs. Here's one that shows me the interaction between load and speed and fuel economy. And this graph over here, which shows me a couple different interactions, including between the name and the economy and the range of the airplane, right? So this is interactions, behaviors, and they're separated. If I merge them together, suddenly I get new behaviors, new interactions. I now also know the interaction between load, speed, and range. That's because there's a new path that got formed when I moved it from the separate hypergraphs into the merged combined hypergraph. This is showing us interactions between different parts of our systems. It's maybe not quite emergent behavior, but it's this part of emergent behavior. This behavior emerges out of the composition of these two hypergraphs. These new behaviors allow us to do simulation paths that don't just go between domains and don't just go between models, but even go between software tools. And this is really cool. I wanted to show this because this is, to me, a brilliant just outcome that happens because of this declarative simulation. So we have, let's say we're modeling this crankshaft for an automotive system. We have a geometry model that shows its mass properties, moments of inertia, weights, things like that. We have an ANSYS model that we use to get the deflections of the crankshaft under various loading simulations. And we have a MATLAB model that's showing its kinematic analysis. All that's information, but in order to calculate that information, do those animations, create that CAD, I have to use these softwares, CAD, MATLAB, ANSYS. All those different softwares operate in different hardware and different requirements. There's lots of different complexities going on with using these softwares. But I can take these models, CAD, MATLAB, ANSYS, FEA, break them into their nodes, and find the functions that relate those nodes and form a hypergraph that fully integrates all these software. So here's the hypergraph. It's a little complex, but don't worry, you don't need to know the details too much. What you do need to see is that every edge that's colored shows which software is calculating that functional relationship. So the blue ones are Python. A lot of these are like algebraic relationships. Python's great at algebra. But we also have MATLAB, which is doing our animations. It's doing some optimizations. Whatever you want to do in MATLAB, you can do it here with these red ones. These greenish yellow ones are Onshape. So we have things like making features, making extrusions, calculating moments of inertia over here. And then we have also ANSYS over here. This is running FEA software. This is creating our deflections, finding our von Mises stresses, whatever it might be. In each case, what we've done is taking these softwares and broken them into the information and the functions for calculating that information. And you can see that if I start with my inputs up here, I can trace a path that weaves through Python, then into Onshape, creates my CAD model, runs an FEA analysis on it, and gives me back information that might tell me, based on these inputs, here's the interaction between geometry, your material properties, and even the kinematic analysis up here to get how much your crankshaft is moving and in what way. That interactions of the system, as calculated by different software, fully captured in the hypergraph. One thing I want to point out is that this is not, the integrating software is not necessarily new, right? We have lots of workflows. If you open up ANSYS Workbench or Model Center by Phoenix, you have lots of different ways to load different softwares and say, calculate something here, pass the information to this model, then pass it to this software, on and on and on. Those workflows exist. The difference that I'm adding here is not inter-software connection. It's declarative inter-software connection. And the difference is that with the normal workflow, you create a digital thread that says, here's the way I want to take information from Onshape to ANSYS and then to MATLAB. I wanted to pass this way. And if you wanted to do a different workflow, you create a new digital thread. Now let's go Onshape to MATLAB to ANSYS. Let's get a moment of inertia here and collect that here. For every single different way you want to integrate these systems, you have to define the digital thread for that. But in a hypergraph, we're declaratively establishing those threads. That means that every single functionality of the software gets represented as an edge in the software. And every single way that you could arrange those edges, those functionalities, those become different paths rather than different models that we have to create or workflows we have to create. So rather than a billion imperative ways to connect our 10,000 API functions in CAD, we get one CHG, and all the paths that come out of it are all those different workflows that we could run. What this does is it makes our digital twins far simpler and easier to maintain, rather than having a rat's nest of digital threads, which is what normally happens when we're digitizing for a company. We have one CHG with all the updates and relationships and interactions stored as paths that are discoverable in that system. I'll also point out a limitation with this. One is that these are not very human readable, and you now know that after looking at all these CHGs. There it can be complex. There's a lot of stuff going on. They're not made to be read by humans, and that's kind of the intent. They're made to be autonomous. They're made to be read by computers. Everything in here is very parsable for a computer. They're not great for discovering behaviors for a human. One of the ways we work around this is that we say these are not really for modeling systems. If you wanted to make CAD geometry, you should do that in CAD. It's far easier to work in CAD and make shapes and all these things. You can make this shape using this hypergraph. This is what the CAD model for this looks like an on shape. It is complex, there's a lot of stuff going on, and it's usually things that you don't have to think about. And when you're doing CAD, you don't want to think about sketch IDs and access tokens and where the dimensionality comes into your bounding spaces and interference calls. The CAD should handle that for you, and it does much better. What we say is use CAD, use Onshape and SolidWorks and whatever to make your CAD model. The trick with CHGs is that they can represent every system. So once you've made it, once you've done the modeling work and figured out those relationships, then you can translate them into CHG. And once they're translated, you get out all of the declarativity, universality, and integration that you're looking for to represent your system. Okay, so that's one of the limitations and one of the ways we work around it. Okay, so that's model-based engineering, the ability to trace out digital threads between domains and even between softwares. The last application, the one that I really want to focus in on, is digital twins. A digital twin is any virtual representation of a real system. That is, I take something that's real and I want to know something about it. I want to use my computer to be able to inform it about that system. The reason we do this on a computer is because it's a lot easier to do experiments on a computer than it is in the real world. If I want to know the length of an airplane, I don't have to go out to the tarmac and get a tape measure. I want to just go to a computer, pull up the digital twin, and get that length off of the digital twin. Much easier on the computer. What we have here, golly, you can't see this at all, can you? That's fine. Let's see, can you see this one? Yeah, let's start here. It's like a little bit easier. What we have here is a demonstration to show that digital twins are not just these ethereal virtual representations. What we have is a digital twin is a real system that we can do experiments on, and that we can actually back out how those systems behave. So I have this really simple demonstration. Here I have two light bulbs that are very fleshed out. One of them is always on, one is always off, controlled by this bidirectional switch over here. And over here I have a counter that can show either 0 and 1 and 0 and 1. So this is a digital system, even if it's not a computer. It has just digital states on it, 0 and 1. What I want to say is that the behavior of these two systems is the same. That is that they are twinned in some way. And this is a unique definition that we're driving with the digital twins. That a digital twin is any two systems whose behavior is identical. That is that you can see, I can map this constraint hypergraph up here for this light bulb system. This says that if light bulb 1 is on, light bulb 2 is off, and vice versa. If light bulb 1 is off, then light bulb 2 is on. The same constraint hypergraph can be written for this digital system. If the first counter is 1, the second one should be 0, and vice versa. The labels are different, but the behaviors are the same. We call that identical up to homomorphism. If we can say that these two hypergraphs, the behaviors that we ascribe to these systems, are the same, then we can say that these two systems are twinned. And what that means is that if I simulate this system, if I say the counter number 1 is 1, therefore counter number 2 is 0, that simulation infers the state of the light bulb system. If counter 2 is 0, then light bulb 2 must be off. So you can see I can do a simulation on the counter side, the digital side, and it infers the information for the physical side, the real side. What we've got here is this very nice definition where we can kind of wrap this all together and say, what's a digital twin? A digital twin is a digital system that has the same CHG as another system. And so now CHGs are into the definition of a digital twin. I've seen lots of researchers from the National Academy of Science and engineers, and also from other researchers around the world even, trying to express this need for a mathematical foundation. There's even a call out for NSF right now to really drive home and say, what does it mean to mathematically represent a digital twin? This is it. A digital twin mathematically is this captured behavior. We've mathematically captured the behavior here and showed how to create this digital twin so that we can represent all of its behaviors. And to really drive that point home, let me give you a demonstration that really deals with the real world complexities. This demonstration is based off of a microgrid that we did for the Naval Postgraduate School. This is the microgrid of here. You have lots of things coming on. You can see we have models for solar panels, generators, data centers, batteries, all these different things that have very unique behaviors and need to be integrated into the single grid so we can see how the energy flows are happening and how the power is being distributed. This is based on an actual physical microgrid based in Monterey, California at the Naval Postgraduate School. You can see the schematic for it over here, the controllers and the solar panels. This is actually installed. And there was a digital twin already made for it. The digital twin that was made previously is here. It's a good digital twin. It's got great behaviors. It's as good as a digital twin as we're going to get usually. What it was, though, is as the traditional digital twins are made, it was made very imperatively. So there's this big long MATLAB script, has several hundred lines in it. We have these Excel files. I think we had like 10 or 11 different Excel databases. And when you press run on this MATLAB file, it would pull in inputs from the Excel tables, process them through all these complicated processes, and then spit out your outputs. Here's what the microgrid is doing, either observing or simulating it. That's great. It works very well. There's nothing against this model. This is hard work done by people at NPS to make these models work. The problem is that because it's imperative, it's really hard to break down the behavior that's coming there. We haven't captured the behavior for the user. You don't know, for instance, if you wanted to turn your batteries on after the generators turn on or switch those around, how you're going to implement that in this MATLAB function. You also don't know if you can turn off some of these things. Can you turn off this if statement? Can you switch it to another order? Can you change the ordering? That arrangement of relationships is not captured in the imperative model. You cannot know that because you don't know the behavior. Otherwise, though, we can take these models that were made in nice MATLAB and Excel and convert them to a CHG. A CHG is complex. I'm only showing a subset of it here. You can't even see the subset. But it's got over 500 nodes, almost 600, 300 edges, lots of partiality, lots of cycles, lots of interesting things going on. But with this, we can integrate all these different models together into a single graph. Algebraic models, dynamic ones, probabilistic models, linear equation solvers, file input-output, database queries, all these different complex domains get brought together, and we see the integration between all of them. Because of that, what we do is we create this very highly functioning digital twin. As soon as it's based on this constraint hypergraph, the implementation on a computer, combined with our solver that we're using, allows you to use this digital twin for anything you'd want to use a digital twin for. That's describing our systems. So if you wanted to observe a state, or if you wanted to simulate a state, that's get captured as the nodes and edges. So here's one where I might say, I want to know what the state of the battery is, I want to know the state of the loads, I want to know the state of the solar panels and everything going on, I want to track it over this much time. You just plug that in, you ask the call, and our solver declaratively, autonomously goes through and builds the program that will create that simulation for you. This creates your digital twin from this really, again, rat's nesty mess of digital threads into one model where you as a user don't have to know anything about behavior. I don't have to make those models. I don't even have to know what's going on with the batteries to be able to say, tell me what's going on with this, tell me what's happening here, tell me how to do this, and it will do that for me autonomously. Our point here is that by establishing the theory of CHGs, really driving the mathematics home and how they work, what we've been able to do is unlock new abilities in this advanced multi-scale, multi-domain, multi-physics, complex systems modeling. Before I end, I want to talk about, this is the work we've done, the papers we published. I want to talk about some of the directions we're going to be taking this in the future. So first off, we've worked out a lot of the theory. There's still always more to do. One of the theories we're working on right now is model selection. Currently in constraint hypergraphs, there's lots of different ways to represent competing models. I showed one with edges, but you can also use viability constraints and also black box and abstract things. We don't know which one is necessarily better or which cases make them better. We're still investigating the best ways to represent them and why they might be better than others. We also are trying to combine these with artificial intelligence, especially large language models and neural nets built into large language models. The idea here is that if you have a digital twin that's this caller, you don't want to have to actually go through and identify all your inputs. I want to, as a human, just go through and say, what's the weather in Bristol today? And have my AI transform that input into a simulation call. The nice thing about this is that the AI is not going to hallucinate information out because it's relying on the CHG for the deterministic information. That information is always correct. And if you use AI to call your CHG, the information it returns will always be as correct as the models in your CHG. Avoids hallucinations, makes your AI much more deterministic, but also allows it to map to the more noisy human-based interfaces we like. And then finally, we're trying to integrate faster heuristics. Right now we're doing that breadth-first search, but if we do a pre-solve based on assuming that all the edges are not partial, that all the edges are fully viable, what you can do is find a perfect path. That's the path that if everything is perfect, will always be the fastest. And you can use that ideal path to kind of use as a heuristic for a way to search that's more of a best first search rather than a breadth first search. The best first search would be much faster and would allow us to actually hopefully choose paths that are more likely to get us to our optimal target without having to exhaustively examine every single path. That's A-star searching over here, and that's what we're hoping to implement. That's ongoing with work on that. Okay, let me summarize what we've got so far. First off, because we have the mathematical structure of a CHG, we can represent any system. We talked about those structures already. Second, once we have a system represented, we can use an intelligent agent to autonomously discover information about that system. Things we've observed, things we want to simulate. That's everything. Everything we want to know about the system can be given to us autonomously. And then third, Once we implement that, we can connect models across domains, across scales, even engineering software to create digital twins and digital threads that are usable, simpler to maintain, and more robust in their implementation. That's our work right here, providing a universal language for declarative systems modeling. It's been a long journey to get here with all this and all the work we've done here, but we're extremely excited with some of the contributions that we made here in terms of providing tools that are actually useful for some of the really complex decisions that we make as engineers and as scientists. And we're excited for where this might go in the future, and I'm excited to carry this forward. And thank you for your participation in this. There also are people online. I don't know if anybody can hear, but if anybody would like to ask questions online, now is the time. We can hear you. My mic's up.
All right. If you will excuse yourselves. Thank you so much for coming.
We've ended the presentation, so we're going to end it here. Thank you for joining us on Zoom, and I'm going to turn off the Zoom meeting. Thank you. Thanks. Thank you.